Okay, hello, welcome. In this video, I'm going to be talking to you about differential equations and reminding you of the stuff that we already learned about them. Now, you're in my Cal BC class and we're really getting towards the end of our material. Really, there's only two more things I need to tell you about, and both of them have to do with differential equations. And so I figured that, the last time we really spent a bunch of time talking about differential equations was, I believe, back in October. And so, it's been like almost 6 months ago, and so maybe we should remind you of the things that you already know. Okay, so I'm going to start off with what is the meaning of the differential equations, and then how did we solve them, okay? And I'm going to do, quite a few examples along the way. There's one thing I won't be able to do on this video. I won't be able to look at a slope field and determine the equation of the differential equation, or look at a slope field and, draw a solution curve, just because I'm limited by technology. So I think the first thing is talking about what is a differential equation. And so that's where we're given the derivative. Okay? So this could look something, like, in the easiest case, f prime of x equals 2x plus cosine x. Okay? I think you could probably think of an f of x that fit that pattern. Sometimes we saw it as dy dx equals, maybe something like x minus y. And these are both differential equations. These were ones, this one was one we were able to solve. This is one that we are not able to solve in this class. But really what it meant was it was giving you, for a given, x value or a given point xy, what's the slope of the curve at that point? Or what's the rate of change at that moment? Okay? And so I think, kind of the first question I would start off with was, taking it all the way back to the beginning of calculus, give me an equation for the tangent line, use it to approximate a value of a different function. So, suppose f is a solution to the differential equation dy dx equals maybe 2x minus 3y. And we know that f is a solution, which means that, it's a function where its derivative satisfies this equation. And, maybe I'll say that I know that it passes through the point 1 and 2. So I could say that f of 1 is equal to 2. And they might tell you something like write an equation for the tangent to the graph of f at the point where x equals 1. Okay. Okay, and you remember how we do this. We need a point and a slope to get an equation for a line. Okay, so I need a point. My point is going to be x is 1 and y is 2. And the slope, I'm going to use this differential equation. That's dy dx is equal to 2x, which is 2, minus 3y, 2 minus 6 is negative 4. So my equation is going to be y minus 2 is equal to negative 4 times x minus 1. Okay. I think another question I can ask you right here, just going off of this, is the graph of f concave up or concave down at the point 1, 2? And we can do that. We're going to need to find the second derivative of f, right? And so that'll be the second derivative of y with respect to x both times. So we'll have to take that derivative implicitly. That's something I want to remind you about. Okay, so if dy dx is 2x minus 3y, then the second derivative of y with respect to x both times is going to be, well, I'm going to take the derivative with respect to x of 2x minus 3y. Okay, with respect to x, the derivative of 2x is 2. And the derivative of y is going to be dy dx. So 2 minus 3 dy dx. Okay, fortunately, I already know what the value of dy dx was at the point 1, 2. I already did that. It's negative 4. I'm just going to use that. And so it's going to be 2 minus 3 times negative 4. So it'll be 2 plus 12. So I'll say d second derivative of y, x both times at the point 1, 2 is going to be 2 plus 12 is 14, and I could conclude that the graph of f was concave up at the point 1, 2. Okay, so that's kind of just, what are a couple of things we can do just confronted with a differential equation. I think, of course, if we were to have found that dy dx was 0 and the second derivative was non-zero, we could conclude that there was some sort of maximum or minimum depending on the sign of the second derivative. That's something I also need to point out to you. But I don't think I want to go through and do a whole example on that because I think that we've had plenty of practice doing that in our discussion of Taylor series. I think next I want to show you what the graph of the differential equation looks like. And this is also somewhat limited by technology, but I am going to pause the recording and try to make a real nice plot here so I can plot a differential equation. All right, now this is a pretty basic example. Sketch the graph of dy dx is equal to x plus y at these 9 points that are kind of centered around the origin. But, I'd kind of need to point out to you that this is a thing that you'll be asked to do on the free response section of the AP exam. And it's usually, about 8 or 9 dots. And what we need to do is we need to get the zero slopes right, and we need to have kind of like the relative slopes right. We don't have to, go through and measure really accurately with a protractor and make sure our angle is right to reflect the slope. We just need positive slopes to be positive and stronger positive slopes to be, steeper than less positive slopes. And the first step, what we're going to do is we're going to make a little chart of x, y, and dy dx, and then we're going to plot that slope at each x, y pair. So I'm going to have x and y and dy dx. Okay, so at x equals 0 and y is equal to 0, dy dx will also equal 0. Okay, and a zero slope is where we're going to just draw, flat. Okay. And I'll point out, it's really good to start with your zero slopes. So let's just try to figure out any place where this is going to equal 0. Well, this will equal 0 if y is equal to negative x. So, if I have x and negative x, like 1 and negative 1, or negative 1 and positive 1, over here along the line y equals negative x, I'm going to have zero slopes. So I'll have 0 again. So over here I'm going to have a flat slope. And then down here, same. Right? And then, I don't know, maybe I'll just look at, I think all of these, or maybe both of these are going to have the slope positive 1, because x is 1 and y is 0. X is 0, y is 1. All right. And a slope of 1, a good way to do this would be, and I was assuming this was 1 unit away, is that, you kind of just aim for this. But like I've been saying, it does not have to be the best thing ever. And so on this one, I'm going to aim down here for a slope of 1 and do a little bit of that. Okay. Ideally those would be parallel. They don't look the most parallel ever, but again, they're not going to pull out a protractor and be like, oh, they're not parallel, you're going to not get your credit. I think both of these, we're going to have negative 1 because x is negative 1, y is 0, or x is 0, y is negative 1. So I'm going to, it's not so bad, y'all can see that. Okay, negative 1 and also negative 1. And then where x is negative 1 and y is also negative 1, the slope will be negative 2, right? We're going to add them together. Okay. And so that just needs to be more steep than either of these. So it's just going to be, we'd want to go towards over 1 up 2. So, you can sometimes do that. Either way, we can just know that it's going to be steeper and negative. Okay? And then over here where x is 1 and y is 1, we're going to add those together and we'll have a slope of 2. And I know that it'll just need to be even steeper than those. But I do have it on there. I'm going to aim towards that. And that should be about good. And here we have ourselves a picture of the slope field. Okay, I think that if you really wanted a picture of, what was happening to a curve that had this kind of slope, you'd need a much larger slope field, right? And the best slope fields are ones that we can get where a computer generates it for us. But occasionally on the AP exam, we have to produce our own small slope field, and that's how we do it. We just start by, figuring out what the slopes are and plotting the slopes just like you would expect. Let me think about what are we going to do next. Okay, you may also be asked to look at one of these and choose an appropriate equation in a multiple choice setting that describes it. And I always recommend going based off the zero slopes, trying to figure out, where are we seeing flat lines on our slope field, and then going and making sure in the equation that those x, y coordinates are going to make your differential equation zero. But I think as far as slope fields go, that's probably about all I'm going to be able to show you, within the confines of the technology I have. So I think next we need to talk about solving differential equations. Yeah, so now let's talk about solving differential equations. I'm going to start with, a nice differential equation that only depends on x, because that's going to be the easiest for us to solve. Right? If we're given the derivative and it's only in terms of x and we want the original function in terms of x, then we're just going to anti-differentiate like we've been doing for quite a while now. Okay? But I also want to point out that this is kind of a vague question. This could mean two different things. Right? On one hand, we could be talking about the general solution. And this is the one that has a plus c with it. Okay. Remember, in general, the solution to a differential equation is probably going to be a family of functions that are all separated by some sort of constant. And so if I'm looking for a general solution, really what I need is, I'm just going to say f of x equals the antiderivative of f prime of x with respect to x, so cosine of 3x dx. Okay. I always like to remind you about this type of antiderivative. Right? Because you know that the antiderivative of cosine is sine. You would expect it to be sine of 3x plus c. But then you're going to need to take a second to be like, wait a second, there's going to be a chain rule implication here. If I take the derivative, it'll be cosine of 3x multiplied by 3 for the chain rule. So I need to prepare for that, because I don't have 3 cosine of 3x in my integrand. But I divide it by 3. So I've got myself a general solution. And then if they want the particular solution, that's going to have to come with an initial condition. Okay? So the general solution has a plus c, and the particular solution has an initial condition. Okay? So we want the particular solution f to the differential equation with, let's say, make it a little more exciting. How about f of pi over 2 is equal to 5? Okay. Well, if we do that, kind of the first step is the same. We take the antiderivative, we have a plus c, and now to get the particular solution, we want an actual function. We're going to need to figure out what the value of c is. So I know that f of x is equal to 1/3 sine of 3x plus c. Okay. But I also know that f of pi over 2 is equal to 5. So f is 5. I'll say 5 is equal to 1/3 of the sine of 3 pi over 2. Well, the sine of 3 pi over 2 is going to be -1. Okay. So c is going to be 5 and 1/3, which I believe is going to be 16/3. And so I can conclude that my particular solution to this differential equation that passes through the point x equals pi over 2 and y equals 5 is going to be f of x equals 1/3 sine of 3x plus 16/3. And that's solving, your straightforward differential equation where it's only in terms of x. We also know that this is not the most common type of differential equation we need to solve in AP Calculus, right? So let me show you one of those. Okay, now this is where we spent the bulk of our time looking at differential equations and working with them, was on separation of variables. And this is really the only technique we have in AP Calculus to solve differential equations. If you're interested in other techniques, you need to take a differential equations class and you'll learn a couple more techniques. And then, you keep going, and there are other places where there are other techniques besides separation of variables in other classes. But for this one, we have a very limited scope. And I do want to take a second. I think I meant to say this at the beginning. But the reason that people would be interested in differential equations is precisely the same reason that people are interested in science at all. Because the closer you look, all of the kind of the rules and the laws of science are pretty much spoken in the language of differential equations. All the way down to F equals ma, kind of like one of the first things you learn about physics, force being proportional to acceleration by mass. And if you think about it, what is acceleration but the second derivative of position? And so that's really what it's saying, is that, it's giving you a relationship between the second derivative of position and the force mass relationship. Okay. Need to start by saying that not all differential equations are separable, right? This one, I can't separate using multiplication and division, right? Separation of variables was where we took everything with x and moved it to one side and took everything with y and moved it to the other side, so that we can then anti-differentiate both sides with respect to this, variable. But this one is not something that we can do that with. You got to be real careful about the addition inside of a differential equation. But I also have to tell you that no one would ever ask you to solve a differential equation in this class that wasn't separable, or that wasn't just anti-differentiable like the one I just did. So, but where people get caught is sometimes they'll give you one that's not separable, and they'll just ask you questions about it, kind of like I was talking about earlier, the tangent line, concavity, max-min stuff, is there a point of inflection, things like that. These are things that I can ask given you a differential equation and potentially maybe a point. Where people go wrong is they will look at this and they'll be like, oh, I've got a point where presumably probably where x is 3 and y is 2, no, say x is 3 and y is 3. Oh no, that would be 2. That's 0 and 2 would give you a 0 slope. And then you could take the second derivative and see if you had a non-zero second derivative and go from there. But actually, no, you could do that with this one. But what people do, rather than running the second derivative test, is they try to find a solution and then take the derivative of that and see if it's going from positive to negative or negative to positive. And that is not the thing to do. Okay, remember that you're only supposed to do separation of variables if they say the words find the solution to the differential equation. Okay, that's my disclaimer. All right, this one is, okay, so as I was saying, this is not separable. Not separable through multiplication and division, specifically because of that. Right, that addition right there. That's a problem for us. But over here, we can separate this, right? I'm going to multiply both sides by dx and divide both sides by y minus 2. Okay, so I've got y minus 2 to the negative 2 power dy equals 1/3 of x dx. And this differential equation, I also forgot to mention, the reason I chose this is that this was from 2018 Calculus AB free response. Okay, so this was not that long ago, an actual differential equation somebody had to separate and solve on their AP exam. But I actually think that this one was pretty friendly, right? Because we don't have to worry about any logs or anything. There will be plenty of practice on separation of variables on whatever kind of problem set I assign for 13.1 in this class. Okay, so kind of the next idea is if two things are equal, then their antiderivatives are going to be equal. So I'll say the antiderivative of y minus 2 to the negative 2 dy is equal to the antiderivative of 1/3 x with respect to x. And then I'm going to do the antiderivative. Okay, bump up the power by 1 divide by the new power, double check for chain rule consequences. Okay, that'll be positive 1, y minus 2 to the negative 2 times the derivative of y minus 2 with respect to y, which should just be 1. This works. Okay, and then over here, we're going to bump up the power by 1 and divide by the new power. So it'll be x squared divided by 2, so I'll have 1/6 x to the 2. Okay, you might be saying, dude, where's the plus c? And I always just put it on the right with the x's because now, I didn't write it out or anything, but usually the instructions, they're very careful with the directions in this class. And so what the instructions on the problem will be like, hey, find me y equals f of x, the particular solution to this differential equation with, f of something is something else. So let's go with, I don't know what the actual solution is going to be like, but I think that if I let x be 1, I shouldn't have to worry about division by 0. And I'm not, super concerned with, being able to figure out c. If it's unpleasant, I can just deal with it. So I'm going to say find the particular solution y equals f of x that solves this differential equation with f of 1 equals 1. I think that will be safe enough that I can find a particular solution without too much trouble. All right, and now, since they say y equals f of x, that's where they're saying that you have to solve for y. Okay, your final answer should be y equals, and then something involving a bunch of x's. And so that's why I put the plus c over here with the x's, because you're going to need to put it over there anyway, so might as well just leave it there from the start. Okay, now I just got to get at solving at this. So I'll just have y minus 2 to the negative 1, which at this point I might just call 1 over y minus 2, when I'm getting rid of this negativity here, is going to be negative 1/6 x squared plus c. Okay? And then if I want to get at y minus 2 and I have 1 over y minus 2, I can flip both sides of this equation. I can take both sides to the negative 1 power, provided that, neither of them is 0. And I got to think that it's not. I'm glad I avoided y equaling 2 in that case. So I'm going to say y minus 2 is going to be 1 over, and maybe instead of writing it as negative 1/6 x squared plus c, I might write it as c minus x squared over 6 to save some room. And then what I'll do is I'll add 2 to both sides, and I'll pretty much be good to go, right? 2 plus 1 over c minus x squared over 6. Okay. But I need to figure out what the plus c is, right? Right. So y is equal to 1, and x is equal to 1. So, okay, I think I can see the, oh no, this is going to be unpleasant. All right, I think I made a poor choice of y here, maybe it was a poor choice of x, I don't know, but I'll figure it out. So, y is equal to 1, and x is also equal to 1. So 2 plus 1 over c minus a sixth. All right, well, I think I should subtract 2 from both sides and say negative 1 equals 1 over c minus a sixth. Then maybe I'll multiply both sides by c minus a sixth. So I'll have a sixth minus c equaling 1. So I'll say c is a sixth minus 1 is negative 5/6. That was kind of my hypothesis when I was looking at it, but sometimes it's better to be sure. Okay, and so now I can say, my final solution is going to be y is equal to 2 plus 1 over negative 5/6 minus x squared over 6. I'm sure there's a better way I can write this. I'm pretty sure I could write this as negative 6 over x squared plus 5, but I'm not going to do that, right? Because we just need something that's equivalent. And now, just to remind you of how these are scored on the free response, these are usually quite a few problems, or quite a few points, which means they're worth multiple choice questions. So we really need to maximize the number of points we can get on this type of problem anytime we see it. Hold on, I need to go get my colored chalk. Here we go. And so I'm just going to, in paint off to the side, kind of show you how this one is scored, and then I'll show you where all the points would come from. Okay, the very first thing always in this problem is the first point is for separation of variables. And then there is always that unfortunate note at the bottom. 0 out of 5 if no separation of variables. And so that means separates variables correctly. So we need to be careful with our algebra, but that would be this one right here, where I've successfully separated my variables. Okay, that's point 1. Okay, the next point is looking like, okay, they're awarding 2 points for the antiderivatives. Okay, each antiderivative is 1 point. So the fact that I over here successfully navigated to this one, that's worth 1 point. So I'm sitting at 2. Over here, this one's 3. Okay, then the next one is going to be, let's see, I can't see on the scoring guidelines what the initial condition was that they used. Oh, that's interesting. They solved for their plus C kind of in this step, which is of course valid. As soon as you write down the C onto the piece of paper, you can use your initial condition to find its value. I usually just like to wait until the end. Constant of integration and uses initial condition. Okay, so having the plus C and trying to solve it. In my case, the initial condition was 1, 1. Okay, so here I have the plus C, and here I used the 1, 1. So this is the 4th point, and then the 5th point is solution. And I think they usually say solves for y. That would be this step right here. Okay. So notice that, if we can separate our variables, get at least one of our antiderivatives right, and still remember our plus C and try to find it, we can get most of the credit on this problem. And we also know that if you get 3 out of 5 points on, the AP Calculus exam, on free response, multiple choice, just if you're collecting credit at a rate of 60%, well, you're going to get credit for the calculus course. We like that. Okay, I'm going to check just to make sure that there's not anything else I need to throw out there, but to my memory, I think we need to be able to work with slope fields. We need to be able to just kind of answer function analysis questions given a differential equation, the max, min, stuff like that. We need to be able to solve differential equations by just anti-differentiating and separating variables, and I'm going to go and check and make sure there wasn't anything else on those homeworks in that unit that I didn't talk about in this video. All right, turns out there was one more thing. We talked about Lhopital's rule in the same unit, kind of because it didn't really fit with anything, and occasionally they will ask you a Lhopital rule question inside of a differential equation scenario, and so I figured I would just show this to you also. All right, so they're going to ask us about this limit, and we know that any time we're confronted with a limit, the idea is we want to just try to plug in and solve. Okay, so what I want to do is I want to consider these separately. Sometimes the way that they grade these Lhopital questions on free response, it varies from year by year. And I actually graded 2 of them last summer, and one of them was graded super strict, and one was not. One of them, though, you did not get the credit if you said it equaled 0 over 0. Okay, if you put arrow 0 over 0, that was all right. If you looked at each of these limits separately and said they equaled 0, that was all right. So what I would recommend doing is just kind of saying, all right, this is going towards 0. That's also going towards 0, right? Because 3x minus 15, where x is 5, that's going to be 0, and f of 5 is 0. So I'm going to use Lhopital's rule. And this is one where we don't have to call on the authority of Lhopital himself by name, but if we don't, then we need to say, if these go to 0 over 0, then I'm going to take the limit of the ratio of the derivatives, and we don't want to say all that. So we're just going to say we're going to use Lhopital's rule, and that this is equal to the limit as x approaches 5 of, we're going to take the derivative, that's going to be 3 over f prime of x. Luckily, we have an equation for f prime of x, that's dy dx. And so this is going to be 3 over 2x plus y. And that's going to be the value of our limit, right? We've executed Lhopital's rule. We showed that each of the top and the bottom went to 0. We took the derivative of the top and the bottom separately, no quotient rule. We plugged in again. We see that we're not going to get something that's 0 over 0 or infinity over infinity. And that's all I got for you for this video.